Today's lesson is going to be about collimation. Here we have a normal shoulder x-ray. Note that we used 72 kVp, 13 mass, and we shot an almost perfect DI of negative 0.10, which means this was a great x-ray. I mean, we did clip the inferior angle of the scapula, but this is a technique class, not positioning, so I let it slide. Now, the big thing that I want you to note is that DAP, or dose area product, is 603 milligrays centimeter squared. DAP is made up of two things, the dose, or technique, and the area of collimation. I want you to pay attention to what happens to the DAP when we open and close our collimation. No one ever really says to decrease collimation. They usually say to open your collimation, but it's the same thing. It means to remove the collimation and create a larger field of view or light field. Now, removing collimation is going to have the same effects on the person and the image. One, it's going to be a lot more dose to the patient, and DAP is going to represent this. And two, it will reduce contrast, making it a lot more gray or longer scale. How many of you have seen a tech who is unsure of their centering on a larger habitus person, so they just open their collimation completely? This is so bad. I always think more matter, more scatter. So a larger body part and more adipose tissue is already going to create a very gray image with a lot of scatter. If we open the collimation completely, we are now exposing that person to a larger amount of radiation and further reducing the contrast, making it even more gray. Now, obviously, time and place. Sometimes we can't use collimation, such as an abdomen or maybe a pelvis or a chest, depending on your hospital's protocol. But I'm talking about anatomy that can have collimation, such as a shoulder. So if our original shoulder shot us a DI of 0 with tight collimation, we rocked it. This is great. If I were to decrease my collimation or open the collimation or remove all collimation, let's think plus minus charts. What's going to happen? Collimation only affects the IR exposure and the contrast due to the amount of scatter produced. So, opening collimation will increase IR exposure but decrease contrast due to more scatter being produced in the larger field of view, making it more gray. But the number one thing open collimation will do is super increase our DAP or patient dose. Let's finish talking plus minus charts. Will opening collimation change spatial resolution or distortion? First, what is your definition of distortion? It is size and shape, correct? It's either from magnification or the body part being elongated or foreshortened that can happen from the tube, the patient, or the IR not being aligned with one another. Sometimes this is a good thing and helps remove superimposition and allows us to see anatomy that we otherwise would not be able to. But anytime we have distortion, spatial resolution is going to decrease. What's your definition of spatial resolution? Spatial resolution is your ability to see fine detail. It's the difference between trying to paint a masterpiece with a super fine tip paintbrush or a huge Sharpie marker. A Sharpie just isn't going to provide the ability to see fine details like a thin paintbrush. So, by opening collimation, will the distortion or magnification or elongation, foreshortening change? No! Spatial resolution and distortion are usually inverse of each other, except when we talk about focal spot size and movement, but that's for another day. So if I open my collimation, this does not create size or shape distortion, and therefore is not going to affect our spatial resolution or distortion, only our IR exposure and our contrast. This last picture, we created super tight collimation of about a 2 by 3 inch field of view. So we increased collimation, made the light smaller. This is good. Will decrease IR exposure because less scatter will be produced, but it will also increase contrast because less scatter will be produced or grays. But the best part is the DAP. The DAP on this collimated image went down to 120 milligrays centimeters squared. 120. Now, I realize this isn't a real radiographic image. It's like a weird cutoff clavicle, but I'm trying to demonstrate to you how tight collimation can affect the image and the DAP. If we have tighter collimation, what's going to happen to the IR exposure? It's going to go down, right? And it did. This picture had a DI of negative 2.83. A negative 3 DI means we are half underexposed to the machine's preferred values. Yet my technique is the same at 72 kVp and 13 mass. But note how much collimation can change the IR exposure or DI and how much it changes the patient dose.